The central limit theorem comes in when that's not going to work, when we have an initial population that is not normally distributed. Okay, and the central limit theorem says for all populations, the sampling distribution of means, which is what we're talking about, approaches a normal distribution as n approaches infinity. This is the actual definition of the central limit theorem. You need to know this, just like you need to know law of large numbers. You will be tested on both. But what does that mean? Because what does n approaches infinity? What does approaching a normal distribution mean? Approaching just means it'll look closer and closer and closer to it. It's saying x bar is going to get more normally distributed. It's going to look more like a bell curve as n gets bigger and bigger and bigger. Okay, so another way to think about that is this statement right here. Rather, we say that the sampling distribution means follows an approximate normal distribution for large n. What we're saying is as n gets really, really big, x bar gets closer and closer to normal. Well, what is really, really big? Kind of what is approaching really, really big? What does getting bigger and bigger means? Well, it just means when n is big, we're pretty dang close to a normal distribution. Okay, so that can be written in symbols like so. For large n, x bar is distributed approximately normal. Same parameters. The mean and the standard deviation there don't change. Notice what we've done here is we've added a dot in on top of that distributed symbol. That means approximate. That's this right there. That approximate is that dot. Important to make sure we know when we're using dots and when we're not. If you put a dot, you're telling me approximate distribution. If you don't put a dot, you're telling me it follows an exact distribution. Notice earlier on the page, we did not put a dot because if we start off with x being normally distributed, then x bar is exactly normally distributed. We don't have to put a dot. There's no approximation. If we invoke central limit theorem, because that checkpoint didn't work, then we have to say that x bar doesn't follow an exactly normal distribution. It follows an approximate normal distribution. What does it mean for your life? As long as it's approximate, we'll still use our table and we'll still use Excel and we'll say it's close enough that it's going to be a rounding error to the third or fourth or whatever decimal place that it's close enough. We just need this approximate normality in order to go to our table. We don't need exact normality. Now, what is large n? That should be your next question. What does that mean? Most textbooks use n greater than or equal to 30 as large. However, you need to understand this is a very rough rule of thumb. This is your last resort. I could go off on side tangent after side tangent about how the worst thing that happens when someone takes a statistics course is they leave the course and all they remember is n greater than 30. And they say, oh, I have a sample size bigger than 30. I can do anything I want. That's just bizarre. Okay. This is just a rough rule of thumb. This is your last resort. The 30 only applies to central limit theorem. It doesn't apply to anything else in statistics. But it's saying that n of 30 is sufficiently large for us to determine an approximate normality application for x bar. But really, I just can't emphasize enough. It's a rough rule of thumb. And so I want to make note here that we say that highly skewed populations require a larger sample size and symmetric populations do not need a sample size this large. It's the idea that 30 is your rule of thumb, but if I know that I have a skewed population, 30 is not sufficient. You need probably more than 40, probably more than 50, maybe 60, maybe 70, depends on how skewed it is. If you have symmetry in your population, you don't actually need 30. 25 would be totally fine. If you have enough symmetry, 20 or 15 or even 10 would be fine. Okay? So we want to check this and we want to say that, do we have X bar approximately normally distributed, yes or no? Well, if I don't know anything about the skewness or the symmetry of my initial population, I fall back to 30. But if I do, I need to use that information. I need to say the problem either tells me in words or in picture that my initial population is skewed and my sample size is 35. And so I don't actually think this holds. I don't actually think I have met the criteria needed for this to work, or I have symmetry in my population. So even though I have a sample size of 25, I have met the criteria because I know that 30 is a rule of thumb and I don't actually need 30 if I have a little bit of symmetry in my initial population. Notice I said before, I said if we have a probability question involving X bar, we're going to say, okay, I need to know the shapes that are spread. So what's the shape of X bar? If X is normally distributed, then X bar is normally distributed. Boom, good to go. Check number two. If that doesn't work, we say, okay, well, what about my sample size? What about my skewness? We look at central limit theorem. If we have a big enough sample size, again, potentially relatively to the skewness, and we get approximate normality, boom, we're good to go. If neither of them work, then we say, hey, we can't say that X bar is normally distributed. And so what that means is when we work the problem, if we go to our normal table or if we go to Excel and find a normal calculation, what that means is that table, that calculation is wrong. Why is that? Because we have said X bar is not normally distributed, but we're using a normal table to find probabilities. We're saying we don't have this bell-shaped curve, but we're using a bell-shaped curve to get our probabilities. So hopefully you can see how that would lead us to an error. Okay, so this is going to be our thought process in working through questions that ask about the probability of X bar. Is we have check one, if X is normally distributed, X bar is normally distributed, good to go, I can go to my normal table. That doesn't work? Okay, number two, is my sample size big enough relative to my skewness? If so, I have approximate normality with X bar, boom, I can go to my normal table, good to go. Neither one of those? Okay, I'm going to go to my normal table because I got to get an answer, but my answer is probably going to be off by a little bit. And this is where I want us to think back to chapter one when we talked about biases. The answer to how is a bias going to affect my answer and how is this going to affect my answer is the same. How big is the bias? How big is this error? How off are you on this sample size requirement? If you're off by a lot, your answer should be off by a lot. If you're off by a little, your answer might be off by a little. And it's the same thing with the biases. So as we start putting these things together, that's a concept that I want to make sure that we're thinking of.